Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine sending end voltage, current, power and power factor of a three-phase medium length transmission line when values of load details and generalized constants ABCD are given. A 220 kilovolts 50 Hz three-phase transmission line delivers a load of 75 megawatt at 0.8 power factor lagging at the receiving end and has the following generalized constants. A equals to D equals to 0.9 at an angle 0.6 degree. B equals to 153.2 ohm at an angle 84.6 degree and C equals to 0.0012 mho at an angle 90 degree. We have to determine sending end voltage, current, power and power factor. Let us first write down the given data. Power delivered to the load PL equals to 75 megawatts, that is equal to 75 into 10 to the power 6 watts. Line to line receiving end voltage via line equals to 220 kilovolts, that is equal to 220 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 220 into 10 to the power 3 divided by root 3, that gives us 127,017 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for power delivered to the load PL equals to root 3 times VR line into IL cos phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 75 into 10 to the power 6 divided by root 3 into 220 into 10 to the power 3 into 0.8, that is equal to 246 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 246 ampere at an angle minus 36.8699 degree. In this case, load current equals to receiving end current IR. Taking receiving end voltage per phase as reference, we can write VR equals to 127,017 volts at an angle 0 degree. We have computed receiving end current per phase IR equals to 246 ampere at an angle minus 36.8699 degree. Given generalized constants A equals to D equals to 0.9 at an angle 0.6 degree, B equals to 153.2 ohm at an angle 84.6 degree, and C equals to 0.0012 mho at an angle 90 degree. Let us now calculate sending end voltage per phase. Vs equals to A times VR plus B times IR. Using values we get 0.9 at an angle 0.6 degree into 127,017 at an angle 0 degree plus 153.2 at an angle 84.6 degree into 246 at an angle minus 36.8699 degree. That gives us 139,658.34 plus j times 29,085.031 volt. This may be written in polar form as 142,654.8 volt at an angle 11.7642 degree. Expression for sending end current per phase Is equals to C times VR plus D times IR. Using values we get 0.0012 at an angle 90 degree into 127,017 at an angle 0 degree plus 0.9 at an angle 0.6 degree into 246 at an angle minus 36.8699 degree. That gives us 178.5 plus j times 21.4424 ampere. This may be written in polar form as 179.78 ampere at an angle 6.85 degree. We have obtained sending end voltage per phase Vs equals to Vs at an angle delta equals to 142,654.8 volt at an angle 11.7642 degree, and sending end current per phase Is equals to Is at an angle phi 1 equals to 179.78 ampere at an angle 6.85 degree. For star connected system, sending end current per phase equals to sending end line current, and line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 142,654.8, which is approximately equal to 247 into 10 to the power 3 volts or 247 kilovolts. Phase difference between Vs and Is, phi s equals to delta minus phi 1. Using values we get 11.7642 degree minus 6.85 degree. That gives us 4.9142 degree. Let us now calculate sending end power factor. Cos phi s equals to cos of 4.9142 degree, that is equal to 0.9963 lagging. Now we shall calculate sending end input power. Ps equals to 3 times Ps into Is cos phi s. Using values we get 3 into 142,654.8 into 179.78 into 0.9963, which is approximately equal to 76.655 into 10 to the power 6 watts or 76.655 megawatt. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to compute sending end voltage, current, power and power factor of a three-phase medium length transmission line when load details and values of generalized constants A, B, C and D are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.